So welcome back, everybody. And it's actually 2 weeks since we met last time because we had a public holiday in between. So I'm going to take the liberty of repeating some of the basic ingredients so that we have everybody on the same page. So the topic this week is about the mathematics of diffusion models, which are extremely popular models, especially for those of you who are interested in imaging. And it's based on the mathematics and the physics of diffusion. And it's one of the more popular generative methods. There are some papers from which I have actually borrowed a lot in the lecture notes here. And one is Calvin Luo's paper, and then there's also Kingma and et al.'s paper on variational diffusion models, which is also an excellent read. Now, for TensorFlow implementations, there is a code, the book by David Foster, which we recommended in the beginning of the semester, has in chapter 8 several nice implementations with TensorFlow of diffusion models. Now, these diffusion models are actually pretty heavy to train, and you will see the program which I have, which uses PyTorch at the very end of the lectures. This is something which will quickly take, unless you can run on GPUs, it's going to take half an hour at least. So I will not run the code during the lecture because it's not going to end. And typically these are normally pretty heavy methods to encode actually. So as I said, I'm just going to give you first a quick overview of any motivation for the diffusion models. So they are inspired by non-equilibrium thermodynamics. We are going to remind you a little bit about Markov chains, because that's what lays as a foundation for a diffusion model. And as we mentioned last time, the diffusion model can be thought of as a set of stacked variational autoencoders. That's a very simple way of thinking of it. And there is something which is actually called a variational diffusion model. And this is the one which we will essentially talk about today. So they are prominent in actually generating high quality images. And what we've seen in the field is that if you think of methods like generalized adversarial networks, which became very popular towards the end of the last decade, there was a huge boost in GANs and the activity with GANs and as a generative method and in image reconstruction, etc. The same kind of boost and widespread optimism is something which took place in the beginning of this decade. So till 23, 24, there's been a huge activity, and you may recognize some of these kind of open source diffusion models like DAL-E. I've been using that one to making images, etc., etc. Sora is another one, and later I'm going to show you some examples of things which have been generated. So the models are actually advanced machine learning algorithms that uniquely generate high quality data by progressively adding noise. And if you go to that textbook by David Foster in chapter 8, there is a nice example about a similarity with a real life experience you can have when you look at systems where you can keep adding noise and then learning to reverse that process. And this has been extremely successful in diffusion models. Now, just to give you a little bit of the background of what we're going to have, and I see that I actually forgot to put on the screen here. So let me just put on the screen here so that you can see what I'm showing here. So let's do that immediately. I just forgot to put it on. For those which are not online, they haven't been able to see my screen. And nobody protested, actually. So if we go back a little bit to the basics of these generative methods, so one of the basic things which we want to do is to generate a probability distribution, P of X. And this is obviously something which has to be larger or equal than 0. So that means that since Z is a constant, phi of X has to be a positive function. because it doesn't make sense to generate a negative probability, right? So the things we have to deal with are things like tractability and flexibility. So models which are tractable are normally analytically evaluated and easily fit to data. However, these models are often unable to describe structures in rich data sets because they're simply too simple. On the other hand, models which are flexible, they can be molded to fit structure and arbitrary data. However, one of the problems with these models which are more flexible is that they often end up with being time-consuming when you think of generating new data. So there is always this kind of trade-off between this kind of conflicting objectives. You want both tractability, and you also want something which is flexible. And the tractability means often you have a nice analytical expression, and with that one, you can generate new events. Being flexible means obviously that you would like this to be applied to more general cases. And as we discussed in connection with Boltzmann machines before the Easter break, one of the problems is actually the construction of that normalization constant. And the typical optimization procedure is us maximizing the probability as a function of some specific parameters. And these kind of calculations are often done by expensive Monte Carlo samplings. And you will see the program which I put online for diffusion models is actually pretty slow. So there is always a price to pay. So the diffusion models actually have some interesting features which we will more or less look at today. So there's an extreme flexibility. You can do exact sampling, and there's an easy multiplication with other distributions in order to compute a posterior. So Bayesian statistics is much of the underlying language. And the model log likelihood and the probability of individual states, this is something we want to evaluate cheaply. So in the original formulation, what you would do is actually use a Markov chain to gradually convert one distribution into another one. And an idea then is to use non-equilibrium statistical physics. And diffusion models, they build a generative Markov chain, which then converts a simple known distribution into a target data distribution using a diffusion process. And we are coming back to that. I want to remind you of some of the things we discussed 2 weeks ago. So there will be some elements of repetition. In particular, I want to remind you a little bit about Markov chains, and in order to use that to mimic what is going on in a diffusion model. So the basic idea is actually to make small perturbations from one step to the next one. And then that means that we will often have analytically tractable functions. Typically, this is a Gaussian we are training, and we are just making small changes to the Gaussians. And since a diffusion process normally exists for any smooth target distribution, this method can actually capture data distributions of arbitrary form. So first, we train a neural network to introduce noise into the data set. And then we methodically reverse this process. So it's basically a two-step process. And I'm going to outline what it means. So the typical thing we do first is obviously to pre-process the data, which means that we will typically do the standardizations. And that is often important for handling noisy image data in particular. So the kind of pre-processing, which many of you have seen in courses like FYS5429, where you actually scale your data in order to avoid large outliers, etc., etc. All these things here are obviously things you have to do. And normally that is something which helps in getting a better training. So what we are going to do now is actually to go back a little bit to what we did on April 24th, 2 weeks ago. And we are going to remind ourselves a little bit about the original autoencoder machinery, and then say a little bit about the Markov chains, and then we are going into the mathematics of diffusion models. So all equations are essentially in here, but I'm going to actually switch back to the whiteboard now pretty soon. So let's do that before we continue. So as I said, there will be some elements of repetition from last time, also because since it's 2 weeks since we met, and most likely some of these things may have been forgotten. At least I would have forgotten it. So I'm just extrapolating my goldfish memory onto you guys. But let's now try to bring up some of the elements which we discussed before in the previous lecture. So if we look back to variational autoencoders, essentially what we want, this is the kind of ideal, we have some probability distribution, which we have labeled as the marginal distribution. And this is given as an integral over a function which depends on some latent feature or hidden variables. This could also be the variables of a standard neural network of the hidden layers. And then we would integrate away those variables. And this is normally called the marginal probability. And what we typically want then is to evaluate a problem. So this P of X, which is now the probability we want to construct by training on the data. This is something which we would typically write out as a function of some parameters, theta. And the optimization problem which we end up with, just to remind you of that, this is some of the basics which applies to all the generative methods. There is no change from Boltzmann machines to variational autoencoders, to GANs, to diffusion models, etc. So we typically end up training with respect to these parameters. So the optimal parameters theta hat are given by us calculating this function P of theta of X. This is the function which we typically optimize. And we know from the product rule in statistics that this P of X can also be written, so P of X of theta, and I'm just going to skip sometimes the value of theta, but I'm going to keep it till now. So this will be given by some P of X of H. So that's the probability of finding X and H divided by what we normally call the conditional probability. So this is the probability of finding H given X. And this is something which, this is called the product rule in statistics. And this lays the foundation for the derivation of Bayes' theorem, which we discussed before the Easter break. So what we typically end up with then is an optimization problem where we now, if we think of variational autoencoders, so let us quickly remind of ourselves about the variational autoencoders. So you would have a domain here where we feed in the input data. So this is X, the data set, which we are feeding in the training. And we just label this as X. Now, this one is then transformed by an encoder, where we then train a probability distribution, which is typically given by a Gaussian. So this renders some of the training easier. So there is an encoder part. And then we have a Q. And this depends on some additional parameters, which we also need to train. And this is the conditional probability of going from X to H. So this reads, as we have said before, and I'm sorry for repeating that, this is the conditional probability of finding H given X. So this is the encoder. And this is used now to reduce the dimensionality of the system. And when we do that, we translate that one into what we call a latent space. And this is normally a space of a much smaller dimensionality where we have some few degrees of freedom which are relevant. So if you think back to the standard autoencoders, we were just reducing the dimensionality of the system through an encoder function, which could be a neural network. And then with that one, we could later reconstruct the data set. So what we're doing now is to train a new probability. And these probabilities, both Q of phi and P of theta, are normally given by a Gaussian or normal distribution. So this P of theta of H, which in Bayes' theorem plays the role of a posterior probability, is then something which in a variational autoencoder is simply trained as a normal distribution with zero mean and a variance which is equal to 1. So that's the latent space, which is defined by this variable H, which we often in Boltzmann machines call a hidden layer. So all these kind of networks have some kind of commonalities where this H refers either to a latent space, or it can also refer to what we call as a hidden space. Then this one brings us back to the decoder part. And now we are using Bayes' theorem. And we produce then a new probability distribution, which is a P of theta, where we now have X given H. And from that one, we produce then P of theta of X, where P of theta has now integrated away the variables H. And this one produces then the variables X tilde, which we're going to plug in here, which are then generated according to this probability P of theta of X. So P theta of X is the probability we want to optimize, and that consists of all these different steps here. So I just wanted to quickly remind you of some of the basic mathematics which we did with the variational autoencoders. And the reason why it's called variational is that the optimization problem has a lower bound. And we proved that last time. And this is called normally the lowest boundary because of the ways you set up the expectation values of the probabilities. So what we are doing then, when we are setting up the variational autoencoder, is that we have this probability of log P of X. And I'm going to skip this subscript theta sometimes. And this quantity here, what we can do then is to rewrite it. So this is it. Sometimes I will skip it. Let me try to keep it. So the way we derived this last time was simply to multiply by 1. That's the first step. And 1 is something we can define as we want. And in this particular case, we define that as a Q of phi of Hx of D of H. And this is a probability distribution which is normalized to 1. So that means that I could now rewrite this quantity. So log of P of theta of X is something which we could rewrite as a Q of phi of H of X multiplied with log P theta of X and multiplied with D of H. So this should be an H. Then we know that we can use the product rule. So I'm not going to repeat all the steps here. So we use the product rule, which means that this P of theta of X multiplied with P of theta of H of X is given by P of theta of X of H. And when we did that and went through some additional manipulations, we could actually show that the final integral we have to evaluate, that means this quantity here now, which is given by an integral, we could rewrite this in terms of, and I'm just stating the result which we derived last time. So I hope you can forgive me if I don't re-derive everything. Now, the H's are then drawn according to this probability, which we normally train in terms of a Gaussian, a multivariate Gaussian. And then we have, so the E here is an expectation value, and we are calculating the expectation value of this P theta of X of H, of Q of phi of H given X. So the Q of phi of H of X is the one which brings us into the encoder, and the P theta of X of H is the one which relates us to the decoder. And then we have an additional term, which is given by H, which is now drawn when we calculate the expectation values because we have an integral. And that is given by log of Q of phi of H of X of P of theta of H of X. What we discussed last time is that we can show that this quantity here is larger or equal than 0. And that gives the name variational to the calculations. So we can do further manipulations, but typically these terms are then evaluated by a Monte Carlo sampling. And we have a model for the Q of phi's here, which are typically given in terms of Gaussians. Now, when we now are going to set up the diffusion models, we can view a diffusion model, in particular the variational diffusion model, as a set of stacked variational autoencoders, where we then are going to vary this function, which is called the encoder function, by small perturbations for every step we make, which then means that hopefully this one will then converge to the correct distribution when we have many steps in the diffusion process. But anyway, this is essentially the kind of basic steps which we end up setting up for our variational autoencoders. And last time we discussed how to evaluate these two integrals. And in particular, since some of them can be evaluated analytically, due to the fact that Q of phi is then given by a simpler model. So if you look back at the handwritten notes from last time and also the lecture notes, you will see the final expressions which we are typically going to calculate. And this Q of phi, just to remind you of that one. So let me just set up. The typical way this is trained is by setting this up to be a Gaussian distribution for H, where we have some mu of phi defined as a function of X here, and then we have a variance, which is also a function of X. So these are quantities which we need to set as parameters. Furthermore, the latent space is normally modeled according to a normal distribution as a function of H with 0 mean value and variance equal to 1. So these are typical functions which are used in the training, and they're also used in the training of a diffusion model. So, but let me now, unless you have any questions, what I want to do now is to give you a quick reminder of Markov chains, because that's going to, in a way, set the scene for how we're going to set up a diffusion model. So a brief reminder, and this is something which we discussed last time as well, but since 2 weeks have gone, it can be okay to actually remind ourselves a little bit on Markov chains. So we know that if we now look at if we limit ourselves to a discrete case, you can transfer this one to the continuous case as well. But what we have is a probability distribution. Let's call this P of I. And now it's handy to introduce time, but time, it doesn't need to be physical time. It could just be you calculating a probability at a given step. You could think of you jumping around in space, and every time you jump around, that is one step you make, and you don't need to relate that to physical time. But having this kind of image of physical time can sometimes be useful. So what that probability is the probability of being in a state I at a time t. And we know that mathematically, this is given, if we now just have discrete events, this is now given by a sum over all the possible states the system can be in. So J here is all possible states. And if you're thinking of you jumping in physical space, this would be all positions which you could access. But we are just going to call them in a more generic way as states. So we are just summing over all these possible states, and then we have a probability for making a transition, which is a stochastic matrix. And this is then multiplied with P of j, and we can say that this is given by a time t minus 1. But it could just be a small time step. Now, we are assuming that this t of ij doesn't depend on time, but it could also be time dependent. So in our case, what we have then is that this t of ij is an element of a stochastic matrix, of a matrix T, which is stochastic. A matrix T, which is a stochastic matrix. A, what we call a stochastic matrix. Now, what we know about the stochastic matrix is that when I sum over all j values of Tij, they sum to 1. So all the columns, if we're now dealing with this discrete case, all the column matrix elements, they sum to 1. What we also know is that the largest eigenvalue, max lambda of T, is equal to 1. So that's the largest eigenvalue. So this is essentially what characterizes a stochastic matrix. So we could assume now that Tij is also time dependent, but I'm not going to do that in this example here. And then what we also have, since these are probabilities, this probability P, if I sum over all the probabilities at a given time, that is also normalized to 1. So that means that if I now look at the time t equal t0, what we would have then would be a p as a vector of t0, which is now simply this column vector where we have a p of 0. This is element 0 of t0. So these are just the given elements of t0. And this goes down all the way down to all the possible states which we can access with this probability. So one of the assumptions when you typically do a Markov chain is that this probability P is known, but the probability T, which then involves a lot of complicated transitions. This can be extremely complicated chemistry, biology, it can be complicated physical reactions. All these processes here are normally just encoded into this transition probability, which we in principle don't know. Now, the way we would model that one, whether we accept a move or not, is something you can set up by sampling rules, like the Metropolis sampling, or you have Gibbs sampling, you have Langevin sampling. So these are ways by which one can determine this transition probability with only a knowledge, which is typically a model knowledge of the probability P. So the typical situation which we end up with then, if we now look at the probability at a given time, so it means that this P of I, which we put up here, of a time t, you can write this as a time t0 plus 1, is now given by the sum, and then we have this mystical matrix multiplied with P of j of t0. Now, a Markov chain is so that when we rewrite this as a matrix vector in a matrix vector language, as matrices and vectors, if we do that, and vectors, you can then rewrite this equation here as a vector P at the time t0 plus 1 equal to this matrix T times a vector P at the time t0. Then, in a Markov chain, when equilibrium has been established, when you let in the limit where t0 goes to infinity, what we have then, if we now let t0 in this limit, we just change it to just t, what we have then is a vector p of t equal to a matrix t times the vector p of t. And since it then becomes time independent, we would typically then, in this limit, we would simply write it as a stationary problem, which then defines the most likely state after a given number of transitions. So this is normally called either the stationary state, the most likely state, or the equilibrium state. So if the process converges in a Markov chain, which depends typically only on the previous step, then this P reaches an equilibrium situation where now we go, sorry, I just repeated what I had previously. So if equilibrium has established, what we have then is that this is now given in terms of a time-independent quantity, P. Now, if we now look at this process, if we assume that T is the transition probability is time-independent, we could actually write this in the following way. So if we now think of P at a given time, T of M, this is something which we can write as T to the power of M multiplied with P at time T0. And this means that the way we can look at these kind of transitions which we are making is as follows. So we can now set up a T0. We can think of having a T1, a T2, etc., till a final time Tm. So what happens then is that we have a well-defined probability of T0 here. We have a probability of P of T1, and I'm skipping the vector signs, if that's okay with everybody. And finally, I have a P of T of M here. And every step here is now given by this matrix, T, which now goes from T0 to T1. So I'm just writing this symbolically, so it's not the strictest mathematical way of writing it. We could assume that this matrix is time dependent, or we could just have it as a time independent matrix. And finally, the final transition here would be something which looks like T of Tm minus 1 going over to T of M. So the thing which we would like to know then is obviously this probability. And it's this kind of machinery which is actually used in setting up a diffusion model. So before we now look at how we schematically can understand the diffusion model, let's remind ourselves about the variational autoencoder another time. So if we now take the variational autoencoder again, let's just do that. So what we have then is our space of input values. This is the data set we are plugging in. We are getting a model X tilde, which is given by this probability which we train. We have this encoder phase, which we call a Q of phi of H of X. This brings us into the latent space of H, where we have a probability model, P of H. And this brings us into the decoder space, where we now train a model for the conditional probability of X given H. So this is meant as a way to reduce the dimensionality. And from here, I produce a P of theta. Now, if I look at a basic operation which we have here, the way you can look at this is now in terms of a P of theta of X. And then we have the product rule, where we multiply with P of theta of X given H, multiplied with P of theta of H, which is called a posterior. And this quantity here is actually the same as the one we wrote earlier, which is a P of theta of X of H. And the probability we want is this P of theta, which is called the marginal probability. Now, the way we are going to look at a diffusion model is as follows. So if we now just keep this image in mind, we can think of us stacking all these encoder pieces on top of each other, and assuming then that we are making small perturbations and small changes, diffusion model. So if we do that, we could think of now having some initial state x0. This is the one which we are feeding in as the training data. We don't know P of x0. This is then fed into a latent space 1. And we can continue like this with different latent spaces till a final latent space, which I'm just going to call H of t. Now, here we are going to set up a transition from the full data set to a latent space, except that now the latent spaces are going to have the same dimension as the original space. So I'm going to have an H1 given x0. I'm skipping subscripts with the parameters to be trained. These quantities, the Q's, are normally set up as normal distributions. And we are going to make small perturbations for each step of a normal distribution. So we are going to get an H2 of H1. And this is going to continue till we reach the final one, where we now have a Q of HT given an HT minus 1, which was the last step here. So this is going to be an H of T minus 1. Then, from that one, we are then going to reconstruct a new probability, which is going to be a conditional probability, which is now a function of H of T minus 1 given H of T. And this continues all the way till we now reach the final one. So we would have a P of H1 given H2. And finally, we get a P of X0 of H1, which is then used. This final quantity is the one which then is used to generate a P of theta of X, which we then are going to use to generate the new events. And we are going to call it X0, generate X0 tilde. And we typically want to have X0 tilde as close as possible as the original X. And a typical way to calculate whether we are close or not is to calculate the mean squared error of the data set which we have. So let's now try to look at more the mathematics of diffusion models. But you see the basics, the reason why we can think of the models as a stacked variational autoencoder. The benefit of a variational autoencoder, as we have it here, is that when we maximize this probability, we know that there is a lower bound, which gives us something which is larger or equal than 0. And that means, again, that having a lower bound, we can then invoke all the elements of variational calculus. We are going to get the same here. So one of the typical diffusion models which are on the market is something which is called a variational diffusion model. And we are now going to look at the mathematical details behind that. So if we now think of these basic steps which we want to have, we are going now to look at or represent the joint distributions and the posterior Markovian variational autoencoder, because it becomes like a variational autoencoder. So one of the quantities which we are going to look at then is a probability of P of x. And then as a function of all these, and I'm going to write this in a schematic way because this h of from 1 to t is now going to represent what we have in the figure here. It's going to represent everything we do from here to there, and then back here again. And that will produce such a probability, which we then can simply write out in terms of the product rule as a p at the time ht multiplied with some parameters. So we're going to have parameters theta of h of, x. Let me just, so this x, which you see here, is generic x, and we're going to specify it in more detail later. But let me just correct that one. So this is x, no, not x0, but x. I'm going to put explicitly in x0 in just a few moments. So this will be given by p theta of x as a function of h1, but then this needs to be multiplied by a product, which now runs like a p theta, and then I have h of t minus 1, and then h of t, and this goes from t equal 2 up to t. Because this will be the product of all the individual probabilities for making these jumps, which you see here. So we go back from here over to that one, and then we continue all the way till we come to the final x. Then we need also to define these functions. So I'm going to define this q, and they can depend on a parameter phi, like we had with a variational autoencoder. And in this case, I'm going to have this to depend on h1, which is the one we are interested in first. And this is now an h1, an h of 1 to t. And this is a quantity which will be defined as a q of phi of h1 given x multiplied with all the remaining ones. So this goes from t equal 2 up to final t, and then I have a q of h of t minus 1. So the final marginal probability which we want is obviously one where we have integrated away all these quantities. So the final marginal probability if you're setting that one up, is obviously we want something which is a log of p of x, which is then given by log, and then I have the integral of p of x, and then as a function of h of 1 to t, so that contains all these steps, and integrated over all h's from 1 to t. So what we are going to do now, after the break, is actually to look at the final distribution which we are going to set up in order to find the algorithm for evaluating the different terms in a diffusion model. And as I said, these terms, q of phi, which you see here, they are typically modeled by a Gaussian distribution. And every time we move one small step, we are assuming that the changes from one Gaussian to another one are so small that they can be treated as perturbations. And by doing this many, many times, the hope then is that these will approach the correct distribution. Okay, I see I'm a little bit over time, or almost on time. So maybe we can take a small break of 15 minutes here, if that is okay with everybody. So what we want now is to set up the equations which we are going to implement numerically. And in the calculations here, just for the notation itself, what I'm going to do now is to replace all the H1, H2, etc. up to HT. I'm just simply going to replace them with X's, so that all the symbols are X's, except that now the final probability we want is X0. So I'm just going to replace this with X1, X2, and this is just for the simplicity of the notation, and X0 is the data, is the input data. So in the notation here, what you will see then is that if we now look at all these events which we have here, instead of having H's, I'm going to call this X0, X1, and then I'm going to have an X2, and finally an XT here. So everything except X0 is going to be the latent spaces. So I hope you can forgive me if I just change notation a little bit, but it's just for a little bit for the notational simplicities, because the integrals are going to get pretty large and contain many variables. So the final probability we want, so we want a model probability of P of X0. So that means that we are going to define a probability now, which is X0, which is drawn from this probability. And I'm going to I will skip now in the notation here. This is subscripts, theta, and phi. Okay? So just keep in mind that these functions which I put out, this function Q, when I write it like a Q of X T plus 1 and Q of X of T. So previously I had H of T plus 1 and H of T. This had a subscript phi. So I'm just keeping that one in notation here. And you will see that when we set up the integrals here, you're going to see why this is convenient. So what we want is to obviously optimize log of P of X 0. This is the quantity we want to optimize. And this is the same as optimizing the integral from X0 to the final time or the final step T multiplied with so we are integrating over all the latent space, all the latent degrees of freedom, latent variables, from 1 to the final T here. So in the previous case, I used H, but now we are just integrating from X1 up to X of T. So we want to integrate away all these degrees of freedom, the latent spaces. Remember now that when we did the variational autoencoder, we had just one latent space. Now we're going to have many such latent spaces because we are going to change these probabilities Q, as we call them, these quantities here, by small perturbations step by step. So if I now write things out, what this is going to be is the log, and then I'm going to have the integral, and now I'm going to have my P of X 0 to T multiplied with Q of X1 to T given X0 multiplied with dx1 to T. So what I've done here is simply putting in 1. So the trick I did was simply to put in, this is equal to 1 in my integral. And we did that when we also looked at the calculation for the variational autoencoders. We just plugged in 1, which was just given by the ratio of the same probability. Then what this is actually a expectation value. So this is log of the expectation value, where now the x's are drawn according to this probability. So I'm just gonna, so the probability which we use to draw the x's from 1 to t with a given x0 is now given by this expectation value of p of x0 to t divided by q of x1 to t with x0 as input. So that's an expectation value, which looks like what we had previously when we looked at variational autoencoders. So when we did the variational autoencoders, we actually used the same trick, except that then we had only one latent variable. And now we're going to have many latent variables. So when we now look at this expression, which you see here, we now have to write out all the different latent variables. So let's do that. So this expectation value is equal to, I'm going to plug in some, this is going to take a little bit more space, the expectation value with respect to these probabilities for the latent variables, 1 to t, given x0. And then I have, and I'm going to continue to the next line, I have p, and then I have my x of t multiplied with the product from t equal 1 up to the final time. And then I have my p, and this is the quantity which we are going to have a parameter on, but I'm going to skip the parameter. So in principle, there should be a parameter theta for these variables, or these probabilities. So this is t minus 1 of x of t divided by, and then I have the product of all the transformations I make up to t, and then I have q of x of t minus 1. So I'm going to suppress this variable in the equations here. There will be a dependence, there will be a parameter which we have to optimize. This again is something which we can further rewrite. So I'm just going to pause a little bit so you get time to write it down. So what I'm doing now is simply to write out the product of all these different probabilities. And this follows very much the same procedures you have when you do a standard Markov chain, where you simply have all the probabilities multiplied with each other. So this is where the diffusion model thinking kicks in. So when you multiply all these probabilities, when you reach a final time, the hope then is that you have reached the most likely distribution. So this is the comparison with the physical process of diffusion and Markov chains. So when we continue along this line, so let's do that. I'm going to have 1 page per equation now because they're going to take a lot of space. So this is going to be given by log. And I'm drawing all the time these numbers with, it's log, not log here, but I'm going to put the log inside. So I'm extracting the numbers according to this model for the probability, which is going to be given by a Gaussian. And you will see later in the notes here. So this is going to be given by a log, and then we have a parenthesis. And I'm going to write this now as a p of x of t. And I'm going to single out p theta of x1 multiplied with t equal 2 up to the final t. And then I have a parameter theta here of xt. I will keep it. And this ends here. This ends here. But then we have divided with q of x of t and xt minus 1 multiplied with the sum, the product from t equal 1 up to uppercase letter T. Like this. Now I can rewrite this term again. So let me just rewrite it here. So it's E of Q of x1 to T of x0. And it has a log and parenthesis. And this is something which I can then rewrite as a P of xt multiplied with a P. Let me keep the parameters, as I said, of x1 here. And then I can rewrite the sum here by writing it as a T equal to 1 up to T here. And this should be P of, so I'm just rewriting P of theta. And then I have x of t plus 1 divided by q of x of t minus 1 multiplied with t equal 1 up to final t of q of xt minus 1. Okay, so let's pause a little bit so you guys can get time to write it properly. You will also find the same, exactly the same derivations in the Jupyter notebook and in the PDF file. These derivations look a little bit better in the Jupyter notebook. It's easier to read them than when you look at the PDF file. So everything you see here is actually in the Jupyter notebook. So if you look at what I did here, just to explain a little bit, the only thing I did was actually to change the summation bar, the variables here. So by changing to t equal 1, then this one obviously becomes t, and then this becomes t plus 1. So in this equation here, I just changed the variables in the product. So if I start at 1 here, then I need to have t, and then I need to have t plus 1 here, which you see here. That's the only thing I did. Then, if I look at these equations, I can rewrite them in terms of 3 different terms. So I can write this out in terms of the following 3 terms. So I can have a term which looks like this is equal to E of Q of x1 to t with x0. And later I'm going to specify what the model is. And then if we now look at the first term, which we have here, I can now, if I look at the different terms, since I have a log here, I can then take the ratio between this one and that one. I can have this term by itself, and then I can have a new term which simply contains that ratio. So at the end, we can write this out in terms of 3 different terms, and these different terms have different names. And we are going to look at that a little bit later. So this is going to be the first term, where I'm going to have a p theta with the parameters of x0, x1. So that is the first term. Then I have the next term, which is q of x1 to t, given an x0, which now has, so these are expectation values which have to be evaluated by Markov chain samplings. So this is a standard Monte Carlo sampling. And that's actually a time-consuming part when you do the calculations here. Then we have the next term here, which is a p of x of t. And that is normally called a prior. And then we have divided by q of xt of xt minus 1. That's the second term. And then finally, if we now look at the last term, which now is coming from this two terms here. Since we have a log here and we have products, we can rewrite that as a sum of logs. So that means that the last term is going to be equal to E of Q, expectation value again, x1, T of x0. And this is now given by the expectation value of this sum, which starts with T equal 1, goes up to T, and then I'm going to set up the final here, which is a log. And this is a log of P theta of x of t plus 1 of Q of x of t minus 1. So we are getting three distinct terms which we need to evaluate, and these are going to be evaluated as expectation values. So all these terms, since the probability has to be larger than 0, it means also that these guys have to be larger or equal to 0. So there are three terms, and so let's try to look at what kind of interpretations we can actually make here. We can actually rewrite this as follows. So let's do that. So this is the final equation, which is the one we would typically encode. So we would have an x1 given x0, and then we have so this is an expectation value, and then we have log of p theta of x0, x1. So this is the one which we need now to reconstruct the final probability distribution. Plus, and this is normally called the reconstruction term. Then we have a new term which will depend only on xt minus 1, xt given x0, and it has log of p of xt divided by q of xt given xt minus 1. So these are the only data points which we need when we are generating that probability. And then finally, we need the term from t equal 1, and then we will have t to minus 1. And finally, it's going to be a q which will depend on xt minus 1, xt plus 1, given x0, multiplied. So this is it now, and this is the expectation value of this quantity of log of a p theta of xt plus 1. So this should be a minus 1 here. So I wanted to do this on the whiteboard simply just to slow down the pace, because if I just list everything in the slides, it's sometimes you don't get all the details. And now I just wanted to go back a little bit to the PDF and the Jupyter Notebook and look at how we actually interpret these different terms. So the first term, which you see here, this one, and I will come back to why this is called a reconstruction term. So this is a reconstruction term. And the reason for why it is called that is something we are going to look at now in more detail. So let's do that and switch to the PDF here. So let me bring that one back again. So essentially the derivations which you see now are basically those which you find here. So the first term, which you have in your notes, is then called a reconstruction term because it predicts the log probability of the original data sample, given the first latent step. So this term also appears in what we have in the variational autoencoders. So this mimics a lot of what we have. The next term which we have is something which is called a prior matching term. And if you look closer at it, this is something which is actually something you can describe by the Kullback-Leibler divergence, and that's why it's written like this. And that is minimized. So we have minimized that one with respect to these parameters theta. That's minimized when the final latent distribution matches the Gaussian prior. So let's just go back to what we had on the whiteboard and just look at that one. So in the calculations here, this term, which you see, this term is now going to be defined by a Gaussian, and it's going to be a prior. So the Kullback-Leibler divergence, if these two guys are getting close to each other, then you have log of 1, and that gives you 0. This term, which you also see here, which also has a name, it's called a consistency term. This term here, when looks also like a Kullback-Leibler divergence, and when these two probabilities are getting close to each other, then this ratio also disappears. So let's look back at the PDF file a little bit and see if this makes sense. Yeah, I need to do that one. Let me just do that, because then it should be able to see it. Here we are. And let me go back to full screen mode. So the second term is then a term which matches the prior, and it's minimized when the final latent distribution matches this P of xt. And this term requires often, it's not always true, but it requires often no optimization. It has no trainable parameters. And as long as we have assumed that when you have large enough T, then the final distribution is a Gaussian. So then you will have two Gaussian divided by each other, which at most is going to give you a constant. So that second term in the calculation, when you do this in many, many steps T, this is a term which often goes to 0. So this is one of the benefits of running this type of calculations. The other thing is that since you're using a Gaussian as a model for these latent spaces, then many of these integrals, or actually all of them, can be evaluated analytically. And that saves a lot of time in the calculations. Then the final term is also a Kullback-Leibler divergence, because we have a ratio between two probability, and is normally called a consistency term, and it attempts to make the distribution at a given time consistent for both the forward and the backward process. So it's normally called, we would typically have a denoising step where we make the image more and more noisy. And it's a denoising step from a noisy image that should match the corresponding noising step from a cleaner image, and for every intermediate time step. So this is mathematically seen in this divergence here. When the two probabilities match each other, then that term goes to 0. So this term is minimized when we train to match a Gaussian distribution. So the training is included in the parameters theta here. Okay, so let's look a little bit at how we actually set up some of these terms. And let's just set up the basics. So the typical distribution in our assumptions. So one assumption is that the latent dimension is equal to the data dimension. This is a difference from variational autoencoders where we actually try to reduce dimensionality. The structure, the latent encoded at each time step is not learned. This is a standard approach, and it's predefined as a linear Gaussian model. So it's a Gaussian distribution centered around the output of the previous time step or the previous step. So it means that you're making a small perturbation for every step for these encoder functions. And the hope then is that when you do this in many, many time steps, it reaches a stable distribution. And this is the final distribution, which is then also a standard Gaussian. So that's the where the diffusion thinking comes in, that when you do just small perturbations, step by step, at the end, you have reached the most likely distribution, which in our case is also going to be a Gaussian. So the distribution of each latent variable, which we call x1, x2, etc., instead of h1, etc., is a Gaussian centered around this previous hierarchical latent. So the structure of the encoder at each time step is not learned. It is fixed as a linear Gaussian model. So what you would typically have then is to parameterize this encoder with some mean values, where you have a alpha here, which functions as a small parameter which changes from iteration to iteration. So that this one would be an 1 minus an alpha of t from the previous step. And this alpha is normally meant then to represent a small change from the previous one to the next one. So mathematically, that means that these encoder transitions are simply defined as Gaussians, where gradually the mean values and the variances changes, but only slowly. So that means that this alpha evolves over time according to a fixed or learnable schedule structure, such that the distribution of the final latent p x of t is a standard Gaussian. And then you can update the joint distribution of a Markovian variational autoencoder and to write the joint distribution for what's normally called a variational diffusion model. And what we have been looking at is actually a variation diffusion model. And a pretty common approximation is that the posterior, which we have, as we did in a standard variational autoencoder, is just a Gaussian with 0 mean and 1 as variance. And this makes it a little bit easier to train the models. So collectively, what this set of assumptions describes is a steady noisification of an image input over time. You progressively corrupt the image by adding Gaussian noise until eventually it becomes completely identical to pure Gaussian noise. So there's actually, this is the kind of process which one is thinking of here. And if you want to read a little bit more, I mean, this article by Luo is actually a very good read. So note also that these distributions are no longer parameterized by a variable phi, since if you think back to what we did with variational autoencoders, we had a parameter phi, since they are completely modeled as Gaussians with a defined mean value and variance at each time step. So in these variational diffusion models, we are only interested in learning conditionals probabilities so that you can simulate new data. And when you optimize this variational diffusion model, the sampling procedure is as simple as sampling Gaussian noise from this px of t and iteratively running the denoising transitions for t steps to generate a new final point x0, which is your final output. And this is what we went through as derivations, and then we have the different terms. So these terms, when we evaluate them, these 3 different terms, they are evaluated by Monte Carlo sampling. That's a standard procedure to evaluate them. I actually wanted to go back to the Jupyter notebook now, so let me just stop that one. And let's move to the notebook. So in a way, this is a kind of crash course. And if you're interested in using these diffusion models, I typically, and I do that every year, if you want to really go into the details of how to set them up, this paper by Luo, which we also refer to in the very beginning, which is this paper you see here, is actually a very good pedagogical paper. And it's actually that one which I've used to make these lectures. So you will find the same equations, the interpretations which we discussed. So So the cost of optimizing this variational diffusion model is normally dominated by the third term, which is this term which we have here. That's the one which is time consuming. As I said, this second term, which you see here, this is often, since it's called a prior matching term, it is minimized when the final latent distribution matches the Gaussian prior. And it normally goes to 0. But the third term is the one which can be quite time consuming. So let me just increase the fonts. So under the derivation which we did, all three terms are computed as expectations and can therefore be approximated using Monte Carlo estimates. However, when you actually study this lowest boundary limit, using the term we just derived, this might be suboptimal because the consistency term is computed as an expectation over two random variables for every time step. Then the variance of its Monte Carlo estimate could potentially be higher than a term that is estimated using only one random variable. So actually this last term is the one which we put up here. This is actually the one which can lead to unstable results in a diffusion model. So here comes some propaganda, which I wanted to say a little bit about. In general, these images which you generate are actually pretty good. The training stability can often be pretty good, and it's often better than GANs, which we will discuss next week. So next lecture, which I plan to be the final one, I had a kind of half promise of looking at reinforcement learning, but I'm running out of energy towards the end of the semester. And I guess you guys also want to do something else. So I will rather prepare that for later events. And if you're interested, I could also direct you to literature on the mathematics of reinforcement learning, which borrows a lot from this statistical / Bayesian way of setting up things. So the thing I wanted to show you, because what we have been doing here is something which is called a denoising diffusion probabilistic model. And the codes which you will find here is a code which I have borrowed from two excellent GitHub sites. There is one here, which I'm linking. So the example which you will find below here is actually an adaptation from these two codes here. So I have not written my own diffusion model, but I actually borrowed from other people. And there are many, many good examples. So if you want to use them, I mean, feel free to, as long as you cite properly, to use what people have developed. So this is a diffusion. If you think of everything we've been going through in the semester here, every single topic, variational autoencoders, Boltzmann machines, diffusion models, this is the research line for hundreds of people. And obviously to write a code like this is not something you do over the night. And that's why if you want to use them, like you're using libraries from scikit-learn, TensorFlow, and PyTorch, use these libraries. As long as you understand the basic mathematics, and that's some of the essence behind the lectures here. I just wanted to show you, there's a nice website here on applications of diffusion models. And if you scroll down a little bit, and you probably have seen some of this is actually a pretty good website. You can see both in music and sound design and animations, diffusion models are extremely popular. And there is one here which is actually pretty amazing. I'm just scrolling down a little bit. So DAL-E is a software I've been using from OpenAI. There's a DAL-E 3, but there's also one called Sora. And if you look at this image here, that is from this movie here, it's actually pretty good. So this is just generated by diffusion models. And there's probably another one, which many of you have seen online, and that's this one, right? I don't know if you've seen that one. When you look at it, it is, if you look at the text here, it's really amazing. It looks like a real person, right? So this is just to demonstrate some of the power of these diffusion models. Okay. So what I've done here, or rather what I have borrowed from other people, this is the more correct way of stating it, is actually a model which is based on, if you remember back when we discussed Boltzmann machines, we mentioned that what is being done nowadays is not to have these simpler functions which we train, but actually to feed in a convolutional neural network. Instead of, in the Boltzmann machine, instead of having a function where you have some simple parameters you vary, that function is replaced by a neural network, a convolutional neural network, and that has been shown to be extremely powerful, for instance, with Boltzmann machines, but it's also being used here. So you will have a kind of neural network, which is at the basis. Then there is a forward diffusion process. So the convolutional neural network is actually the one which is used at each step to define the images and model the images. And then you have a forward diffusion, and then there's a reverse denoising. And we have a training loop. And then when you've trained the model, you are going to sample from the training model and see if the images which you get look reasonable. Actually, the code I have here uses a lot of time, and it took more than half an hour to run on my laptop here. So this UNet is actually a type of convolutional neural network that is used for image segmentation tasks. So you will often see, and if you remember also back to what we discussed in connection with autoencoders, just the plain ones, not the variational ones, there as well, you could have complicated neural networks or deep learning methods as the encoder part and the decoder part. So you're not limited to just have a simple, thin neural network. So what is done here with this forward diffusion part, so that adds noise over t time steps, is that you have this, you corrupt the data by adding Gaussian noise over a sequence of time steps, and then you learn to reverse this noising with a neural network. And then the corruption schedule is typically linear, or even cosine invariance. And during training, the network is optimized to predict the original noise added at each time step. Okay, I see I'm running a little bit out of time. So next week, I will start with a reminder on diffusion models and say a little bit more about the code here. But feel free to take a look at it, and you will most likely see that it's going to be slow. If you go into as well at the textbook by David Foster, which I mentioned in the beginning, you will find diffusion models implemented with TensorFlow. So this is a PyTorch implementation. And we will just say a little bit about the diffusion models, the programming next time, because I see we are running out of time here. And then we are going to jump into generalized adversarial networks, and that will be the last topic this semester on generative methods. So I was hoping to go through this one, but I will talk a little bit more about that next time before we switch to GANs. But feel free to take a look at it. And let's see, there's also a message here. Yeah, this is a comment from here. So GANs are painfully sensitive to the quality of the annotated data. And that's also something we will discuss next time. So diffusion models have actually been favored compared to GANs. But at the end, it's actually you who has to decide which one is the best model for your data. But these four models, which we are going to look at, we have GANs next week. These are some of the more popular generative methods. And I would say diffusion models are perhaps some of the really more popular ones when it comes to sound generation and image generation.